So what exactly is a motion model? Well, let's talk about the kind of motion that we've seen in the first couple days of class, which is constant velocity. Motion models are about patterns. In the Lego Vehicle Bot Lab, most people saw this pattern when they put down position markers. And remember, these were markers along a position axis measured in centimeters. And this position axis had an origin, or a zero marker. And these markers represented the position of the bot at specific times. And most of you marked it every 1 second. So perhaps we had data something like this, and what we know about constant velocity motion is the distance traveled each second is consistent. It's the same. This pattern allows us to predict what would happen if the object were to keep going, and to predict where it is perhaps at in-between times if necessary. This type of diagram is called a motion map. And we'll be using these to interpret a motion that we see or are given, and perhaps to solve problems. A simplified motion map is often used where we just need the starting and ending point, and if we assume it's constant velocity motion, then really just need to know a couple of things to be able to calculate other things of interest. Another pattern that we will use often in problem solving are patterns on graphs. Persistent time graphs also show a pattern for constant velocity motion, which we know is linear. And if you know some things, like say the starting position and how long something was in motion, you might be able to figure out its final position at 10-second mark in this case. Again, that's if you know the slope of this graph, which is the average velocity. Also, velocity versus time graphs have a pattern that says constant velocity, and this graph can also be used to make predictions or calculations. Patterns on graphs lead to equations. This graph here shows constant velocity pattern on a position time graph, where this would be the initial position, and here would be the final position of the object on the x-axis. And then when we look at the motion as time increases, there is some final time. Of course, the 0 would be the initial time. And we know that the slope is the average velocity, and that equals the rise, which is some change in position, over the run, which is some change in time. So average velocity can be written as change in position over change in time. And that's an important quantity, a position versus time graph. Also, just a general expression relating back to the equation for a straight line, because that's what we have here. We don't have y, we have x for position, and the slope is the average velocity as we just calculated. We don't have x, we have t for time, and our y-intercept is actually the initial position. What this equation says is that take some time t, which can be anywhere on the time axis. We can know from this equation what the exact position x is if we multiply by the average velocity and add to it the starting position. So you should realize that this line is really just an infinite number of possible times and corresponding positions, and that's the beauty of the equation, is it gives you any point on the line. X and t are variables, they change, and v and initial position are constants. They are the same all the time for this motion, so these things work together to relate position and time in a very particular way. And just to make note, if the time in this case is the final time, then the line in the equation tells us that the position we calculate will be the final position. Now this is a special case, one instance, and we don't write that in general. In general, we just leave t because it can be any time, and x because it can be any position. This is the initial position, this is the starting position. It doesn't change for a given motion, as well as the average velocity. If it's constant velocity, that will also be a constant. So besides representing motion by describing it in words, we have a diagram, or a motion map, a graph, position time or velocity versus time, and an equation coming from the graph. In this case, this equation derived from the position time graph. These things represent the motion, and we use them to problem solve. Together, these patterns that we see here are our model for constant velocity motion. And as a whole, we refer to these as the constant velocity particle model, or Cvpm for short sometimes.